Welcome to Techie Wise. In today's video, we are going to discuss about the Fermat's and Euler's theorem. So it is primarily used for primality testing. Yeah. So we know that 3 is a prime number, 7 is a prime number, 17 is a prime number, 19 is a prime number, 37 is a prime number. But the cryptographic techniques depends on very large prime numbers. So in that case, yeah, it is not possible for us to manually deal with the primality testing process. So we need a theorem which is Fermat's theorem. So what is that theorem? If P is prime and A is a positive integer, the constraint is A is not divisible by P, then A power P minus 1 will be congruent to 1 mod P. So here, if P is prime and A is a positive integer not divisible by P, then A power P minus 1 is congruent to 1 mod P. So in that case, if I want to check whether P is prime or not, then I should choose a positive integer A in such a way that it is not divisible by P. Then it will satisfy this particular condition. So let us take, so here our thing is, I want to check whether P is prime or not. So let us take the value of 19. Yeah, we know that P is prime. So it should satisfy this condition. So we have to take any random value A. Here in this case, I am considering A is equal to 7. Yeah, it satisfies this condition. 7 is not divisible by 19. So it should, so now we have to proceed with A power P minus 1. A power P minus 1 in the sense 7 power 19 minus 1, which is 18 mod 19. So we have to compute 7 power 18 mod 19. In turn, we have to get 1. So if we are getting 1, then we can be sure that P is prime. And so now we are going to check it out. So 7 square, we are going for the modular exponentiation process. So 7 square, yeah, you can use your calculators, but here we are considering the value of P as larger number. In order to manually deal with, we are considering a smaller value, but in real time, P will be a larger number. So 7 square mod 19. So what is 7 square mod 19? 49 mod 19, which is 11. Now squaring up both the sides, 7 power 4 mod 19 will be equivalent to 11 square mod 19, which is 121 mod 19. That is 7 mod 19. So again 7 power 8 will be equivalent to 7 square mod 19, which is 11 mod 19. So next, if we are proceeding further, this is 7 power 16, which is 11 square mod 19, which is 7. So we can stop it, because if I am proceeding further, then I will end up with 7 power 32, which is not of my interest. So 7 power 18 is equivalent to 7 power 16 plus 2. So 7 power 16, 7 square mod 19. So what is 7 power 16, which is 7 square is 11. So 77 mod 19, which is equivalent to 1 mod 19. So here 7 power 18 is congruent to 1 mod 19. So by this we can prove that 19 is prime. Alright. Next we can move on to discussion of Euler's theorem. So here, before dealing with Euler's theorem, we should have an idea on Euler's torsion function. So in Euler's theorem, we will be using this function, which is represented by phi of n. Euler's torsion function phi of n. So what is Euler's torsion function? Number of positive integers less than n and relatively prime to n. So let me repeat, number of positive integers less than n and relatively prime to n. So by convention, phi of 1 is equivalent to 1. So we can start with an example. So it is a numeric value. So phi of 5. So values less than 5 and relatively prime to 5. What is relatively prime? GCD of A and B is equal to 1, in the sense A and B are relatively prime. So values less than 5 and relatively prime. So I have to check for all the values that is less than 5. 1, 2, 3, 4. Right? So now I have to check for GCD of 1 and 5, GCD of 2, 5, GCD of 3, 5, GCD of 4 and 5. So what is GCD of 1 and 5? 1, 2 and 5, 1, 3 and 5, 1, and 4 and 5 is 1. So what is the count? So what is phi of 5? So 1, 2, 3, 4. So phi of 5 is 4. And now try it out with phi of 8. So what is phi of 8? Values less than 8 and relatively prime to 8. Now try it out with just let me list out the values. So 1 and 8. Yeah. So 1 and 8 is 1. GCD of 1 and 8 is 1. 2 and 8? No, it is not relatively prime. 3 and 8? Yeah, it is relatively prime. 4 and 8? Not relatively prime. 5 and 8? Yes. 6 and 8? No, it is not relatively prime. 7 and 8? Yes. No, that's it with. Right? So less than 8. So what is phi of 8? Phi of 8 is equivalent to 4. Right? So now you can try it out with phi of 35. So now let us list it out. Values less than 5 and less than 35 and relatively prime to 35. So 1 is, 2 is, 3, 4, 5 no, 6 is, 7 no, 8, 9, 10 no, 11, 12, 13, 14 is not relatively prime. 15 is also not relatively prime. 16, 17, 18, 19, 20, not relatively prime. 21, no. 22, 23, 24, 25 is not relatively prime. 26, 27, 28, no. 29, 30, no. 31, 32, 33, 34. Right? So now how many values? So phi of 35 is equivalent to 24. Phi of 35 is equivalent to 24. Now phi of 37. Here we are going to use a property. So here the 37 is prime, right? 37 is prime. So all the values, so less than 37 will be relatively prime to 37, right? All the values less than 37 will be relatively prime to 37. So how many values less than 37 in the sense? 36 values 1 to 36 will be relatively prime to 37. So 36, phi of 37 is 36. So what is the general convention? For a prime number p, phi of p will be equivalent to p minus 1. So if p is prime, then phi of p will be equivalent to p minus 1. So if p is prime, then it is easier task. If p is a non-prime number, then in that case you can see for even 35, I have to list this many number of values, which is not a possible task. As discussed earlier, we will be dealing with very larger values when we are proceeding with the cryptographic technique. So it is not possible. So here it is just a 2-digit number. Think of a 4-digit, 5-digit, 6-digit number. It is not possible to deal with this task. So we need a methodology to compute phi of n. So if I want to compute phi of n, if n can be factorized into prime numbers, if n can be factorized to prime numbers, then, so let us consider n is factorized to prime numbers p and q. Then that is n is equal to pq, right? Then in that case, phi of n is equivalent to phi of pq, isn't it? So this is equivalent to phi of p into phi of q. So p minus 1 into q minus 1, right? So now we can see this example, phi of 35. So 35. So phi of 35. So now 35 can be factorized into 7 into 5, right? So now phi of 35, how I can deal with? Phi of 7 into phi of 5. So which is equivalent to 6 into 4, which is 24. We are getting the same value. So this is how we can proceed with the task. So now we can have a discuss into the Euler's theorem. So what is Euler's theorem? So here, for every a and n that are relatively prime. So here a and n are relatively prime. Then a power phi of n will be congruent to 1 mod n. So if I want to check whether a and n are relatively prime, then in that case I can use the Euler's theorem. Yes. So we can start with the example. A is equal to 3, n is equal to 10. Yeah, we know that 3 and 10 are relatively prime. So this should satisfy this particular theorem, right? So here phi of 10. What is phi of 10? As discussed earlier, we can factorize the n value and then proceed with the task. So it is equivalent 5 into 2, right? Phi of 5 into phi of 2, which is equivalent to 5 minus 1 is 4, 2 minus 1 is 1. This is 4. So now a power phi of n, that is 3 power 4, should be congruent to, so I have to find 3 power 4 mod 10. So what is 3 power 4 mod 10? 81. So 81 is congruent to 1 mod 10. Yes, it is getting satisfied. So now we can see one more example. A is equal to 2 and n is equal to 11. So phi of 11. So phi of 11 is equal to 10. So 2 power 10 mod 11. You can try it out. So 2 power 10 is 1024. So 1024 is congruent to 1 mod 11. So by this we can prove that 2 and 11 are relatively prime. 2 and 11 are relatively prime. So that's it with the Fermat's and Euler's theorem. Thank you.